Hi everyone, Mr. Schleicher here, and today we will be learning about naming ionic compounds. So when we're naming ionic compounds, we want to name ionic compounds. That's the goal here. But before we start naming ionic compounds, it's very useful to kind of understand the theory behind ionic bonding. So first of all, with any bond, we did say that compounds were when we had two atoms that were chemically bonded to each other. So they're held together by this chemical bond. With ionic compounds in particular, there is there's a certain attraction between the positive protons in our nucleus and our negative electrons that are around the nucleus. And just like we have this attraction that kind of keeps these things together, with ionic compounds, they're held together by this attraction between a positive ion and a negative ion. Something else you need to know is that the positive ion is known as a cation, and the negative ion is known as an anion. So one way you can kind of tell them apart is that positive ions, cats, they have pos. So positive ions are cations. Cations are positive. And then anions are the other one. Okay, so how are ions even formed? What are ions? Well, ions are formed when you have a regular element, like maybe a metal or a nonmetal. And these atoms, they're going to gain or lose electrons. Until they obtain something called a noble gas configuration. And it's very important that you know that term, noble gas configuration. So the thing about noble gas configuration that's important is that there's 8 valence electrons, otherwise known as an octet of electrons, which is a really stable state. And when atoms are stable, they're really happy. They don't want to gain or lose any more electrons. There is one exception here. Helium is so small of an atom, it can only fit 2 valence electrons. So for helium, it only cares about 2. It doesn't need the full 8. So what's the difference between metals and nonmetals? So make sure you know that the difference between metals and nonmetals in the first place. When we're looking at your periodic table, it might look something like this. For the purpose of this lesson, metals are everything on the left side of the periodic table. Okay, this is just the shape of the periodic table I'm drawing. And then nonmetals are everything kind of on the top right side of the periodic table. And then you might have some metalloids in between. Don't forget that hydrogen up here in the top left is actually a nonmetal, so you have one nonmetal up there on the top left of the periodic table. So whenever you have a metal, metals are going to generally lose electrons whenever they form an ion, whenever they ionize. And when they lose electrons, they're losing something that's negative. So if you lose things that are negative, that means you become more positive. So they become positively charged. And we know that the positively charged ions are called cations. And nonmetals, they tend to be a little bit more electronegative. They will attract electrons more strongly than metals. So instead of losing electrons, in order to achieve a noble gas configuration, they tend to gain electrons. Just from other elements, or electrons that are just around them in general. When they gain electrons, you're gaining something that's more negative. So you become negatively charged. And we know that negatively charged things are also called anions. Okay, so let's kind of look at this in practice. Let's compare what a regular element might look like compared to the ionized, the ion form of that element. So for instance, a calcium atom, if you look in the periodic table, and you're trying to look up the number of protons, we say the atomic number of calcium is 20. So it's 20 protons. And in the past in this class, we've said that, well, if you have 20 protons, maybe you have 20 electrons. So let's write that. And we said that elements tend to be neutral or they have zero charge. So let's say it has zero charge. We're going to skip noble gas configuration and come back to it. The Lewis dot structure of calcium, we kind of touched upon this, but I really want to make sure we get it now. When you're drawing a Lewis dot structure, it's actually quite easy. You just draw the element symbol in the middle there, and then you draw a certain number of dots around it, the number of valence electrons, or the electrons in the outermost shell around that symbol. And you can tell how many electrons, how many valence electrons are going to be just by looking at the group number on the periodic table. So calcium is in group 2A, so it's going to have 2 electrons around it. So we can just draw 2 dots around that symbol for calcium, and that is known as the Lewis dot structure. Now, for the calcium ion, the ion, since it's still calcium, it's still going to have 20 protons. However, it's going to lose electrons since calcium is a metal whenever it ionizes. So when calcium loses electrons, you want to ask yourself, well, how many electrons is it going to use or lose? And your hint comes from the number of valence electrons that calcium has. Calcium, whenever it loses electrons, it's going to lose all of its valence electrons as a metal. And since it had 2 valence electrons, it will lose 2 electrons. So your total number of electrons in a calcium ion is going to be 18, since you lost 2 electrons. Now, the other thing about losing 2 electrons is you're going to get a positive charge whenever you lose 2 electrons. Whenever we say, what is the charge of something, it's usually quite straightforward. You just count like the difference between the protons and electrons. So in this case, the charge is going to be 2, and we have to ask ourselves, well, is it positive or negative? And in this case, it is a positive 2. So in chemistry with ions, we tend to put the plus or the minus after the number. So we would say the charge is 2 plus. So how does that affect the Lewis dot structure of calcium? I mean, we're still going to draw Ca for calcium, but these 2 valence electrons that we drew before, they're gone. So we don't draw them anymore. What's underneath that valence shell is a full, stable, noble gas configuration. There's like 8 electrons in the shell below, but we don't draw that. What we're going to show, though, is that calcium has a 2 plus charge. So the way we do that in chemistry is we put a 2 and a plus sign on the top right there of that calcium ion. And that's how you draw the Lewis dot structure. So that's an example of a metal losing electrons. For a nonmetal losing electrons, what you're going to do, for a nonmetal, you're going to ask yourself, okay, if it's a nonmetal, am I going to gain or lose electrons? And nonmetals, they're going to gain electrons. So when we look at Cl on the periodic table, Cl is number 17, so it has 17 protons and 17 electrons and probably 0 charge. So you're probably never going to see pure Cl or chlorine or pure calcium out in the world. They're so reactive that they'll probably bond with something else. Maybe they'll ionize first as well. But if we were to see pure chlorine, then maybe we'd say, oh yeah, the symbol for chlorine is Cl, and then when I'm drawing dots around it, I look at the number of valence electrons. So when you look at chlorine, you'll see it's in group 17 on the periodic table, or 7A. So when we're thinking of number of valence electrons, we don't look at 17, we look at that 7A, and that tells us that it has 7 valence electrons. So we will draw 7 dots around the chlorine. And in general, in terms of what's the style of things like this, we tend to pair things up first. And then if we have an odd number, maybe there's going to be a dot that's all by itself. Now let's consider, what does Cl look like when it ionizes, when it becomes an ion? So since it's still chlorine, it's still going to have 17 protons. However, it is going to have a different number of electrons now. So we said that whenever we gain or lose electrons, our atoms are trying to reach a noble gas configuration. So if they were to do that, that means they need to have 8 electrons in their outermost shell. So right now chlorine has 7 electrons. So if it were to try to get 8, it needs to gain 1 electron to reach 8. So if it gains 1 electron, then chlorine is going to have a total of 18 electrons after that happens. So if you only gain 1 electron, your charge is going to be 1, because you have 1 more electron than normal. And since you gained an electron, since you gained something that was negative, this charge is going to also be negative. So we tend to write this charge as 1 minus, or just a minus sign for some people. And whenever we do the Lewis dot structure of chlorine, now we're going to show that we gained an electron by drawing 8 dots around it instead of 7. So the other thing about the chlorine is we want to draw the charge on the Lewis dot structure, but sometimes it's kind of annoying to draw this charge with all these dots around. So we tend to put drawings in chemistry in brackets just to kind of like show this whole thing is like one thing if we want to show the charge. And then the charge can go on the top right. So with this, we said the charge was 1 minus. So some people, many textbooks, for instance, they'll just do a minus sign, and the minus sign does mean a 1 minus charge. So either way would be correct. So something I want you all to notice here in terms of what is going on with the electrons is that notice that calcium, it had 20 electrons before, then it lost 2, and now it has 18. So 18 electrons is a good noble gas. It's a good noble gas configuration here. Chlorine, it had 17 electrons, it gained 1, and now it has 18. Okay, so both of these atoms ended up wanting 18 total electrons. So if we were to draw the electron configuration of what that looks like, for calcium, we might say something like maybe argon comes before calcium, and then we had 4s2 as like the noble gas electron configuration. So then we saw there, okay, yeah, look, we have 2 valence electrons there, 2 electrons in the highest shell number, or shell number 4, and we saw that in our drawing right there. If we draw that of the ion, like what's going on with the ion, well, we could say, okay, we lost these 2 electrons, they're gone. There's no 4s anymore. The 4s electrons are gone. So it's really just the exact same configuration as the noble gas of argon. So if we were to draw the noble gas, the electron configuration of something like argon, normally we go to like the noble gas that comes before argon, like neon, and we say everything that comes after neon all the way up to argon. So in this case, that would be something like 3s2 and then 3p6. So in this respect, we can also kind of look at, everything in the highest electron shell or energy level. And we see that, well, in shell number 3, we have 2 electrons and we have 6 electrons. We have 8 total valence electrons. We're not going to draw that in the Lewis dot structure for cations, but just know that this is a full satisfied octet, and that means that the calcium 2+ ion is in a very stable and happy state. For Cl, excuse me, for Cl, we can also do something similar here. The electron configuration of Cl, we normally look at a noble gas that comes before, something like neon, and whenever we start putting the electron configuration after neon, we will have something like 3s2 and then 3p, and then it looks like chlorine is like the 5th element in that p block, in that p subshell. So we'll say 3p5. And you can see here, if you add up the number of valence electrons, you have 2 and you have 5. So 2 plus 5 does equal 7. You had 7 valence electrons. And you can see here, oh yeah, we had 7 dots around there, that Lewis dot structure. For the chlorine ion, we said we gained 1 electron. So basically, our configuration looks exactly the same, but instead of saying 3s2, we're still saying 3s2, but instead of saying 3p5, we can add 1 electron to that 3p subshell, and it's going to look like 3p6. So notice that 3s2 and 3p6, they add up to 8 valence electrons. 2 plus 6 is 8. And we drew 8 around our drawing. And something else I want you to notice is that whenever we look at this electron configuration, it is identical to this electron configuration. Whenever we're gaining or losing electrons, and we have the same number of electrons as another ion, we tend to call this the same electron configuration. And if you have the same electron configuration, one vocab term you might see used sometimes is isoelectronic. Iso meaning same, electronic meaning electrons. So this just means same electron configuration. We're not going to use that term too much in this particular lesson, but we will see that term come up sometimes in this chemistry class and other more advanced chemistry classes. All right, so that's basically all the information I wanted you to kind of know about forming cations and then forming anions. So whenever you have a metal and a nonmetal and they come together, usually we'll have something like the metal gives the nonmetal some electrons, the metal becomes a cation, the nonmetal becomes an anion. And then you form an ionic bond. The ionic bond is when we have some sort of force that holds that positive and negative ion together. And this force we tend to call electrostatic force. That is the attraction you get from having a positive charge with a negative charge. It's really similar to kind of like the behavior of magnets. Okay, so something else we'll have to do with naming ionic compounds is we'll often have to predict what the charge of certain elements might be if they ionize. So often, it's just really easy as a shortcut to kind of go through this, go through the periodic table and just remember what charge is going to have. You can always conceptually go back and think, if I have this many valence electrons, and I'm a metal, how many am I going to lose? Or if I have this many valence electrons as a nonmetal, how many am I going to gain to get to 8? But in general, you can think of these shortcuts as group 1A metals will tend to have a positive 1 charge, a 1 plus charge when they ionize. Group 2A tends to have 2 plus. Group 3A, usually 3 plus. Group 4A, it could be 4 plus. Sometimes it also is 4 minus. It just depends. Group 5A, okay, now we're in nonmetal territory. So we're trying to gain electrons until we reach 8 valence electrons. So if you have, something like nitrogen is going to have 5 valence electrons and it will gain 3 valence electrons in order to get to 8, an octet electron configuration. So it will have a 3 minus charge after gaining those 3 valence electrons. Group 6A and 7A are really similar. 6A is going to gain 2 electrons and have a 2 minus charge. Group 7A, or halogen group, is going to gain 1 electron when they ionize and have a 1 minus charge. In group 8A, these are noble gases. They usually do not gain or lose electrons, so it will be very rare to actually have a charge on them. All right, so given all that background information, let's go ahead and try naming some ionic compounds. Our most basic ionic compounds, ionic compounds with metals with a fixed charge, these are going to be things that are in group 1 or 2 on your periodic table, or many people also consider silver, Ag, zinc, Zn, or aluminum, Al, to also have a fixed charge. So, if you have any metal like that, you can use these naming rules to name your compound, but the rules are really simple. So basically, when you have formulas like this, you simply say the name of the first element. You get this name from looking it up on your periodic table. And then you say the name of the second element. But with the second element, you're going to cut off the ending of that element name and change it to "ide." Normally, I recommend just getting a feel for it, because whatever you feel is right is most likely right when it comes to like cutting off the "ide." But if you're in doubt, you can always kind of use this table of information to show, oh yeah, that's where I cut off the ending and change the ending to "ide." So for an example here, NaCl. Na is sodium. We just write the name. Cl, that's chlorine, but we're going to change the ending to "ide, so we're going to say chloride. Okay, awesome. So NaCl is sodium chloride. Li2S, Li is a group 1 metal, so we're allowed to just use these simple rules. It is a fixed charge. So Li is lithium. We just write lithium. And then S is sulfur. So we're going to change the ending to sulfur and get something like sulfide. So this Li2S is known as lithium sulfide. All right, let's move on to Be3P2. So Be, or beryllium, is in group 2, so we're allowed to use this shortcut naming. Let's just write down the name of beryllium. It's kind of long, so don't feel bad about having to look at your periodic table for the spelling. And then P is phosphorus. Many students accidentally change the ending and say, oh, this must be phosphoride. But it's actually not. Chemists decided that's too long to say, so we actually say phosphide. And that's how we change the ending of phosphorus. So Be3P2 would be known as beryllium phosphide. Okay, let's move on to naming ionic compounds with variable metal charges. And by the way, whenever we say binary, we just mean there's two different things in there, like a metal and a non-metal. So whenever we're looking at a metal that's not in group 1 or 2, for example, most of our transition metals, the vast majority of our transition metals, they're going to have more than one possible charge. And some people might say, oh, they have variable charges. In this situation, whenever you name these ionic compounds, you're going to have to use Roman numerals. So whenever you put a Roman numeral in the name, this is to help you out, because if a metal has multiple possible charges, you're going to want to say what charged metal it is in the name. So the Roman numeral is what indicates the charge of the metal in the compound. So just quick review, what are the Roman numerals for all the main numbers? If the metal has a charge of 1+, then you write the Roman numeral for 1, which is just I. 2 is II. 3 is III. And then 4, 5, and 6, we're going to use the V notation. So 4 is IV, because V means 5. 5 is V, and then 6 is VI. So notice with the Roman numerals, if it comes right 1 before 5, we put the I before the 5. And if it's 1 after 5, we put the I after the 5. Okay, so like we mentioned on the last page, whenever we had these fixed charges, we can name them really easily. We don't need to worry about all this Roman numeral stuff. Anything in group 1, we know the charge. It's always 1+. Anything in group 2, it's always going to be 2+ charge. These 3 metals, silver, zinc, and aluminum, you're always going to know the charges of them. You don't really need Roman numerals. Aluminum, one way you can remember that these 3 metals you don't need Roman numerals for. First of all, they're kind of like all in the stair-step case on your periodic table. I would take a second to to look at your periodic table, and you would notice that wherever you see silver, zinc is on the top right of it, and aluminum is on the top right of that. Another way you can remember the charges of these is that aluminum is in group 3B, zinc is in group 2B, and silver is in group 1B. So you can kind of think about, oh yeah, the B group number is also the charge. Now, the metals that do need a Roman numeral in the name, things we'll have to figure out what the charge is based off of the formula, is any other transition metal. Just anything in the middle of the periodic table that's not what we already mentioned. Anything from vanadium to manganese to iron to copper to nickel. All of these will need Roman numerals. Okay, so how do we figure out the number of Roman numerals? Well, this very important concept whenever we look at these formulas is that in an ionic compound, all of your charges, all of your positive charges are going to cancel out all of your negative charges. Basically, if you actually mathematically add it up, everything adds up to 0. So everything totals up to 0 charge. So let's look at some examples here. By the way, many people have their own way of solving this. I'll just show you one possible way. It doesn't mean it's the only way. If you found a different way in a textbook or a different YouTube video, then use that way if it works for you. This is just the way I've always done it. So hopefully my way kind of helps you learn how to assign Roman numerals. Okay, firstly here, we have MnO. I'm already thinking oh wow, this kind of looks like it would be manganese oxide because Mn is manganese. And O is oxygen, which we would change to oxide. However, we have to hold up because manganese is a transition metal. We don't know the charge of manganese. We need to put some sort of Roman numeral here to show the charge of manganese. So the way we'd figure out the charge of manganese is we would kind of look over here and just know that the manganese's charge adds up to the oxygen's charge to add up to 0. So what I recommend you do is you look up at the oxygen or the anion and you look up the charge. Oxygen is in group 6A, so it will probably have a 2- charge, 2- whenever it's an ion. So you have to think to yourself, okay, what's going to cancel out a -2? And probably a +2 will cancel out a -2. So manganese here probably has a +2 charge to cancel out the -2 charge from the oxygen. So whenever we're naming this compound, we need to include the fact that manganese has a +2 charge. So the name of this is actually manganese 2 oxide. All right, next one here. This one actually starts getting a little bit more complicated, but you just got to keep track of your numbers and you should be fine. So for Cu3P2, once again, Cu, or copper, this is something we don't know the charge of, but we can figure it out by looking at the anion, the phosphorus. So phosphorus is in group, it's in group 5A. So 5A nonmetals tend to gain 3 electrons and have a 3- charge. So we know each phosphorus, it's in group, if we look at our periodic table here, phosphorus is right here in group 5A. So you can think about it as having 5 valence electrons and trying to get to 8 valence electrons, which means it needs 3 valence electrons. So it's going to have a 3- charge. Or you could think about it as you need to go 1, 2, 3 spaces over to the noble gas column, which means it's going to have a 3- charge. Remember, your nonmetals always gain electrons to become a negative charge. So each phosphorus is going to have a 3- charge. Now here's where the logic comes in. You have to take into account that there's 2 of these in your analysis here. So if there's 2 of these 3- charges, that means in total you have 3 times 2, which is a 6- charge. Now we said before that all our total charges, they do have to add up to 0. So if we're looking at our total charges, just know that if there's a -6 charge on one side of the compound, then that means the other side of the compound has to be giving you a +6 charge. So in total, we have to have some sort of +6 charge that is canceling out this -6 charge. That means that these copper ions, the Cu, it has to add up to 6 plus. If there's 3 of them, you have to think to yourself, what charge times 3 gets me to 6 plus? And the answer to that is going to be 2 plus. So that means every individual copper has a 2 plus charge. So whenever we're naming this compound, we are going to use this charge of a single copper ion in the name as a Roman numeral. So the Roman numeral is going to be 2. It's not going to be 3. Remember, the Roman numeral is a charge of a single ion. Also, the Roman numeral is not going to be 6. It's not the total charge. It's just a charge of a single ion. So when we're naming this compound, let's use that name copper. So copper. Right next to copper, we can do this Roman numeral 2. And then phosphorus is that P. Let's change the ending to "ide." So this will be phosphide. So notice here that this is the name. It's read aloud as copper 2 phosphide. Just a nitpick here. There's no space in between the copper and the Roman numeral, but there is a space between that metal and the non-metal in the middle there. That's just kind of how you write the name. All right, let's look at our next example. And by the way, if you feel like you're starting to kind of get this, I recommend you pause this video, try the next ones on your own first before you see if I'm doing it the same way. It's always better to actively engage with these kind of videos rather than just kind of like passively watch. So you learn a lot better that way. Okay, so in this example, it looks like we have copper once again. Cu is copper. Se is selenium. So, selenium's over here, number 34. Copper's number 29 here in our periodic table. The thing you have to be careful about with copper is that it's not in the section of elements where you know the charge. You might think to yourself, oh, I know the charge. I solved for it. It's 2 plus. However, that's not always the case. Because the charge of copper is variable, it might be 2 plus, but it might not be 2 plus anymore. So you do have to solve for this every time just to double check. So let's look at selenium, the Se, to see what the charge of that is. If we're looking at our periodic table, you'll see that Se is in column 6A. So that means it's going to have a 2 minus charge. It wants to get to 8 valence electrons. Right now it has 6. So it gains 1, 2 valence electrons to have a 2 minus charge. Everything in column 6A will have a 2 minus charge. Okay, so selenium, 2 minus charge. It looks like we just have one of them. So the total negative charge from selenium is equal to this -2. And that means that canceling out that total negative charge is a total positive charge. So the total positive charge is coming from the copper ions. It looks like there's 2 copper ions. So you have to ask yourself, well, what does the charge of every individual copper ion have to be if there's 2 of them that add up to a +2 charge? And the answer to that is probably going to be something like a 1 plus charge. And you can write this as a 1 plus, or you can write it as a single plus sign, but each individual copper has a 1 plus charge. So they add up to a total of 2 plus. Okay, so notice here, this copper, it did have a different charge than that other copper. So it just goes to show you have to solve for this stuff every single time. In terms of naming this stuff, we're going to use that name copper, we're going to use that charge of 1 plus, and then we're going to use the name selenium. So try to name that, and then pause the video, and then the answer here is probably going to be something like copper 1 selenide. Okay, so notice that the ending of selenium became "-ide", the copper has a 1, and the name is So. Okay, let's try the next two examples. So here we have cobalt 2, wait, sorry, I can't read it like that. So we have cobalt, there's 2 of them, then we have sulfur, and there's 3 of them. So over here, we don't know the charge of cobalt, we don't know the Roman numeral, so we need to solve for it. So to do that, remember the total charges have to add up to 0, and we get this information from the nonmetal, sulfur. Sulfur on our periodic table, sulfur is going to be right here in column 6A. So that means it has 6 valence electrons. It's going to go to 8 valence electrons when it ionizes. So it's going to gain 1, 2 valence electrons. So it will have a 2 minus charge when it's an ion. So the sulfur ion will be S with a 2 minus charge. Now, this is where we have to be logical. There's 3 of these S's, of these sulfide ions. So a 2 minus charge times 3 of those, the total negative charge here does have to be a -6, which means on the positive side of things, that must be canceled out by a total positive charge of +6. So you ask yourself, okay, cobalt, there's 2 of them, somehow 2 cobalts add up to a +6 charge. If that's the case, then each cobalt must be some sort of +3 charge, because 2 of those +3s will add up to a +6. So the Roman numeral, remember the Roman numeral is not how many metals there are. The Roman numeral is not the total charge. The Roman numeral will be the charge of an individual metal cation. So cobalt and sulfur is what we're using in our name here. So the name of this compound will be cobalt 3 sulfide. So notice the sulfur became sulfide as well. Our final example is this PbO2. So in order to name this, let's figure out what Pb is. If you look on your periodic table, Pb is right here. It's number 82. It is lead. Since it's in the metals category of things, it's on this side of the zigzag line. Since you might think, oh, it's in group 4A, it must be a 4 plus or 4 minus or something. Well, that's not always the case. We don't know that, so we do have to double check here. Lead can have a variable charge. So let's look at this oxygen here. Oxygen on the periodic table, it looks like it's in 6A. So another element that's going to gain 2 electrons when it ionizes, so it will have a 2 minus charge. So we know oxygen has a 2 minus charge. Now there's 2 of these, so the total negative charge is -4, which means the total positive charge must be this +4. Now this one's a pretty simple example because there's just a single lead ion. The single lead ion has to add up to a +4, so the lead ion must have a +4 charge. So when we're naming this compound, it's going to be something like lead 4 oxide. All right, let's look at the last section of our notes here. In our final section of naming ionic compounds, we have non-binary ionic compounds. So the non-binary just means that there's not just 2 things anymore. Now we're going to have 3 or more different atoms in our ionic compound. Now these aren't actually that much more complicated. You just have to know how to be able to recognize these things called polyatomic ions. The reason why polyatomic ions are called polyatomic is because the poly means there's more than one atom in there, and the atomic, of course, is talking about the atoms. In your class, on your tests, on your quizzes, In this class, we're not going to make you memorize all the polyatomic ions, but there's two of them that are much more common than the others. So these are two examples of common polyatomic ions. Nitrate, which is NO3 with a 1 minus charge, and ammonium, which is NH4 with a 1 plus charge. So these are written a little poorly, actually. So I would correct this if it's not fixed on your paper. Nitrate is NO3 with a 1 minus charge. So what that means is that in a single nitrate ion, there's 1 nitrogen, there's 3 oxygens, and the entire ion has a -1 charge. So that's what that means. It does not mean there's 3 nitrates. It's just a single nitrate ion looks like this. It's like a group of ions. It has to stay together. Ammonium, it is NH4 with a 1 plus charge. So that means there's 1 nitrogen in a single ammonium. There's 4 hydrogens in a single ammonium. And the entire ammonium will have a 1 plus charge. Okay, so that's what that means. So these are two things that if you're able to recognize, it speeds up a lot of examples. For everything else, on your reference table for this class, you're going to look on the back of the periodic table reference materials. So in class, it looks like the other side looks like this. And on the very leftmost side, we do have this list of polyatomic ions. Okay, so here are the ions we're going to talk about in class. You see here, the names are on the left side, and then we have formulas on the right side with possible charges in the top right. We probably will not refer to any polyatomic ions that are not on this list, but there are more polyatomic ions that do exist out in the world. Okay, don't worry about the rest of this page for now. Just worry about the leftmost column with the names, formulas, and charges. So in terms of, how do you look at this ionic compound formula and come up with a name? Well, you always want to split up into 2 parts first. There's only ever 2 parts to a name. There's the first part, the cation, and the second part, the anion. So I guess there's 3 different situations you might have here. You might have a metal and then a polyatomic ion, okay? Now when you have a metal, just remember sometimes they need Roman numerals, sometimes they don't. You might have a polyatomic ion like ammonium and a nonmetal. So if you have a nonmetal, that's not a polyatomic ion, just remember to change the ending to "ide." And finally, you could have 2 polyatomic ions together. Whenever you have polyatomic ions, you always keep the name as is. If the second thing in your compound is a polyatomic ion, you do not change the ending to "ide." You keep the name as is. Okay, and sometimes you'll see there's like multiples of a polyatomic ion in the same formula. If that's actually really nice for naming because you can clearly see where the polyatomic ion is because there's going to be parentheses around it like this. Like you'll see the polyatomic ion formula will be in the middle of the parentheses. You'll have some parentheses around it, and you'll have a number on the bottom right showing that there's that many of that polyatomic ion. Okay, so let's try practicing some naming here with these 4 examples. Whenever you're naming things with polyatomic ions, you always want to split things up into 2 parts first. For example, this thing has 3 different elements in it, which tells you, I think there's a polyatomic ion in here. So you want to identify that if you can, and then you know that everything else is not a polyatomic ion. In this circumstance, nitrate is a really common polyatomic ion, this NO3. So that's the second part of our compound, which means the first part is just Na. So when we're naming, we're only going to name 2 different things, Na and the NO3. So first of all, Na, if we look on a periodic table, Na is right here in our column 1A metals. So if it's in column 1A, you are not going to need a Roman numeral. So you just say the name of Na, which we saw there was sodium. NO3, I do recommend memorizing NO3 because it's so common, but you can always look back on your list here. NO3 has the name nitrate on your list, so you can simply put the name nitrate on that for your name there. So the name of NaNO3 is sodium nitrate. In this next example, you do have to figure out, what are the two different parts here? We have N, we have H, we have Cl. So you can look at your list of polyatomic ions for a while, but if you memorize what NH4 is, you know that this is a polyatomic ion, which means the Cl is its own thing. So we want to say the name of NH4, and then we want to say the name of Cl. So NH4, if we look on your list of polyatomic ions, I think it's towards the top here, that is going to be ammonium. So we are going to say the name ammonium here. And the second part, it looks like that's a chlorine. Cl is chlorine, but you do change the ending of that since it's I. So ammonium chloride is the name of NH4Cl. In this next part, you will see that it looks like there's a lot of things going on here. We have, 4 different elements here. However, the parentheses do make things easy for us because now we know that this is one part, and the second part must be everything else. So NH4 is one part of our name, and the other part is SO4. So we saw in the last question, NH4 is ammonium, so that's the first part of our name. And then in terms of SO4, you will probably have to look that up. SO4 is down here towards the bottom. You do have to be detail-oriented because SO4 and SO3 look very similar, but we're talking about SO4, which is sulfate. So this compound is called ammonium sulfate. Okay, final example I want to do with y'all. We have FeCO3. There's 3 different elements in here, so you do have to be kind of careful. You might have to look for a little bit. Do you notice any polyatomic ion? Like, do you see anything that looks like FeC, or do you see anything that looks like CO3? And by the way, this stuff does get a lot easier as you do more practice. You naturally begin to recognize what is a polyatomic ion and what isn't. So when we look at our list and you're kind of looking through here, you might notice that there is this CO3, and that is carbonate. So that is going to be one part of our name. We have this carbonate there. That means the other part of the name is the Fe. So Fe, we know in our periodic table, Fe is iron right here in the middle. However, you have to ask yourself, okay, if it's a metal, do I need a Roman numeral or not? Well, iron is not in our group 1, it's not in our group 2, it's not silver, zinc, or aluminum. So we do need a Roman numeral. So Roman numeral for iron, the way that we get that, and this is a skill many students kind of struggle with, is you do look at the other part of your compound. And the other part of your compound is this CO3, is the carbonate. Carbonate is going to be a second part of our name, but we do want to look back at that carbonate just to double check some extra information. We want to know the charge of carbonate. And if you look at carbonate, there's 1 carbon, there's 3 oxygens, but the charge of a single carbonate is 2 minus. That'll be really important when we're solving this puzzle. For a 2 minus charge, we know CO3 has this 2 minus charge. We know the total negative charge here, since there's a single carbonate, is 2 minus, which means the total positive charge must be a positive 2. Since there's only a single iron ion here, that means that that iron ion must have a positive 2 charge, which means that the name of this compound is iron 2 carbonate. All right, so that should get you pre-prepared for all the scenarios we might see. Lots of them have polyatomic ions. Some of them have metals that you need a Roman numeral for, but some of them don't. And then I don't know if we have any other particular situations. So on the practice problems I gave you all to try out, for those of you who just have the video right now, I'll kind of scroll past slowly so you can kind of do all the practice problems here for practice. And then you could Google these names in order to check your work, or you can check the answer key I posted for y'all. But in terms of this practice problems, you just want to use the rules that we learned about. I'll do a couple with you right now just to like get you started. But for instance, if we have something like SrSO4, I already thought, okay, Sr is like some metal. SO4 is one of the polyatomic ions. So those are the two parts here. Sr is strontium in the second group of our periodic table, right here. So that means I don't need a Roman numeral for it. I just say the name strontium. So I say, no, I don't need a Roman numeral. It is strontium. And then SO4, for SO4, I just have to look up where that is here. And, it's something that we saw before. This is a common polyatomic ion sulfate. So this is called strontium sulfate. Okay, and just to do another example with y'all, here we have FeCl3. Just two parts here, but the only thing you have to ask yourself is Fe, do we need a Roman numeral for that or not? Fe is a really common metal, iron. It's probably one of the most abundant metals on Earth. Iron is kind of right here, smack dab in the middle of the transition metals, so we probably will need a Roman numeral for it. So we're going to have to figure that out. Yes, we need a Roman numeral. Let's figure it out. It's iron something. We figure out the Roman numeral by looking at the second part here, the chlorine. Chlorine is over here on the right side of our periodic table in group 7A. Whenever it ionizes, it'll probably gain 1 electron. So it's going to have a 1 minus charge. So over here, I'm just going to talk about this really quick. Since there's 3 chlorines, and each one of them has a 1 minus charge. You can write some work here if you'd like. Chlorine has a 1 minus charge. That means in total, it has a 3 minus charge, which means on the positive side, you're going to need a positive 3 charge. Since there's only a single iron, it must have a positive 3 charge. So the name of this one is iron 3 chloride. So that's the general strategy we're doing here. All right, y'all, I hope I helped y'all out. In terms of, anything you're still having trouble on, I recommend, just ask questions of whoever your chemistry teacher is, use ChatGPT, Bing AI, Google things, what have you. I'm sure there's some explanations out there, but the main way you get better at this is practice, practice, practice. All right, I'll see you on the next one.